Does anybody have homework questions? Here we see in section 7.3 in this picture three-dimensional fractals. So these three-dimensional fractals are formed by taking the shape of the face out of each face straight back until those shapes meet in the center and continuing on that way, just like we did with the Sierpinski triangle. So we saw a number of ways to create fractals. The Sierpinski triangle we created by removing space, and that's what's being done here with the platonic solids. Your author opens the section with the question, what is the dimension of a cloud? What is the dimension of a cloud? So let's review dimension, and then you can tell me the dimension of a cloud. So when we looked at zero dimensions, we could only find a point, right? That's all there was in zero dimensions. There was no freedom of movement, no information to locate the position. What was one dimension? So just a line, right? In one dimension we had a line. So we have length. Two dimensions, we have length and width. And we can represent that in a cube, a square rather. So two directions of movement, length and width. So you can think of the paper as being a two-dimensional object if it had no thickness whatsoever. Three dimensions, where we live, has thickness. So we have length, width, and thickness. And we can draw a cube in 3 dimensions, but since we're drawing on a two-dimensional plane, it's kind of flattened out. So I'll just put a 3D object there, okay? So the marker is 3 dimensions. It has length, width, and thickness. So what about a cloud? What would you say the dimension of a cloud is? It has a little thickness to it, right? So it's not two-dimensional. But on the other hand, it lacks the solidity that a marker has. Like I can measure the thickness of the marker. A cloud, where does the cloud begin? Where does it end? How would you measure its thickness? It's kind of vague. It kind of drifts apart. We have the same problem with our fractals, looking at their dimensions. For example, the Koch curve. So we created the Koch curve in class, and it has infinite detail. If we were able to zoom in on it, we would see infinite detail, which you can see displayed in Wikipedia. So what dimension is the Koch curve? Does it have length like a line? Yeah, so it does. It has the length like a line. But does it have thickness? I mean, the edge is kind of fuzzy. The edge is kind of fuzzy like mold on a bread. Who remembers what our definitions of dimension were? Does anybody remember?
degrees of spatial freedom of movement or how many pieces of information to locate a position.
Good. So we had an informal definition of number of degrees of freedom of movement. Number of degrees of freedom of movement, or number of pieces of information to locate a position. So if we look at a cloud, we look at the degrees of freedom of movement, you can move in 3 directions for a while, but then when you get to the edge of the cloud, or even some spots in the middle, are you still in the cloud? Are you not in the cloud? Same thing with the Koch curve. Oh, I got these little Koch curves. The Koch curve has this kind of, it's definitely a line, I mean we drew it, but then it also has sort of a thickness going on to the edge. So does that mean it has a little bit of width to it? We need a better definition of dimension, and that's what we're going to do in section 7.3. We're going to find a better definition of dimension, a formal definition, not an informal definition. So that's what we're going to do today. So let's take a look at 2 dimensions. We have a square in 2 dimensions. Let's see how many copies we take on our square to make a square twice as big. So we'll start with a square. We're going to see how many copies it takes to make a square twice as large. Okay, so if I put 2 squares down, is that twice as large as the first square? In one direction it is, right? But not in the other direction. Okay, so we better add some more squares. It's not square anymore. It's a rectangle that has one direction longer than the other. Four copies. 4 copies. Now the square is, the new square is twice as big as the original square. How about to make how many of these original squares would it take to make a square 3 times as large? So this was 4 copies to make a square twice as large. And now how many copies to make a square 3 times as large? So if I just put 3 out there, that's 3 times as long, but it's not a copy because it's not square. I'm going to add another row of 3. Still not square. So how many copies do we need? Yeah, good. 9 copies. You need 9 copies. In our class, we have had several life lessons. The one in this section is to start with simple and familiar. So we all agree a square is 2-dimensional. So we're starting with that before we move on to things that are a little harder. Start with the simple and familiar. And another thing we learned is to quantify, right? To count. Never underestimate the power of counting. All right, so that's in 2 dimensions. Let's do the same in 3 dimensions. So we start with a cube in 3 dimensions, and then we see how many copies we need to make a cube twice as large. Twice as large in all 3 directions. So how many copies to make a cube twice as large? So I'll stack the cubes up, and I'll stack up 4 like we did with this 2-dimensional space there. So if I stack 4 cubes up, is that going to be twice as large as the original cube? Is this sufficient? Is that twice as large? It's twice as wide, twice as tall. Is it twice as thick? No, it's not twice as thick, is it? Okay, so we need another row behind it. Well, I can't really see the row behind because I'm drawing this on 2-dimensional paper and I'm trying to picture blocks stacked up. How many copies of blocks did I stack up there? 8 copies. Okay, so in 3 dimensions, it takes 8 copies of the original cube to make a cube twice as large. Let's see about 3 times as large, and I'm going to leave a little more space here. Okay, so 3 times as large. So we might as well start with the 9 blocks stacked up. I think it's nice to use a straight edge at this point. It's getting kind of messy otherwise. Where's my straight edge? So we're visualizing this by making it, and that helps us think about how many copies we have. So, drawing the thickness, that's not so easy. Okay, so I need to be 3 times as thick also, so I'm going to stack 3 layers of these cubes. Again, I can only see one face completely, and the other two faces I can see kind of slanted. I can't see inside the cube, I can just see the outside of three faces. How many blocks are there? How many cubes are stacked up here to make it? Yes?
27.
Good, 27. So there's 9 in the front layer, and then another middle layer of 9, and then a back layer of 9. Okay, good. So 27 altogether. Okay, so we're seeing differences between the dimensions. 2 dimensions to make something twice as big took 4 copies. 3 dimensions took 8 copies. To make something 3 times as big in 2 dimensions took 9 copies. But in 3 dimensions, it took 27 copies. That's a lot more. Let's see if there's a difference in 1 dimension. That should be easier. So we just start with a line segment. Make a line segment twice as large. You just need 2 copies. That's pretty easy to see. So less than in either of the other 2 dimensions. And to make a copy 3 times as large, that just takes 3 copies. So there's definitely differences between the dimensions if we look at how many copies it takes to make something twice as big or 3 times as big. Let's go ahead and write that down in a table and see if that gives us some clarity if we put all the numbers together. So we'll write down what the original object is and the dimension of the object, we'll write down the scaling factor of the object, and the number of copies needed. The number of copies needed. So we might as well go in order of dimension. So we took a line, which is 1 dimension. And we made it twice as big, and it took 2 copies. Then we did another line, which is 1 dimension. This time we scaled it 3 times as big. So our scaling factor is 3. It took 3 copies. And we started with 2-dimensional objects. So we started with a square. Its dimension is 2. We made the square twice as big. When we made the square twice as big, it took 4 copies. And then we took a square, which is 2 dimensions. We made it 3 times as big. And it took 9 copies. We took a cube, which is a 3-dimensional object. So we're taking objects that we are all 100% sure on what dimension they are to come up with our our formula for dimension here. So everybody agrees the line is 1 dimension, square is 2 dimension, a cube is 3 dimension. Then we made the cube twice as big. How many objects? That took 8 copies. We took a cube, which is 3 dimensions. We made it 3 times as big, and that took 27 copies. There is a pattern here. Can anybody see what it is? Mm-hmm.
It's kind of like the cube square root, like, so like, for example, 2 squared is, the square is 4, and then
2 squared is 4, good.
And then root 3 is 27. And then
3 cubed is 27, good.
And then 3 squared is 9. And then
3 squared is 9.
And then 2 cubed is 8.
2 cubed is 8. Perfect. That's exactly what we were looking for. So that is what we see. 2 to the 1, 2 raised to the 1 power is 2. 3 raised to the 1 power is 3. 2 raised to the 2 power is 4. Because remember what that means. When you take like 3 to the 2nd power, 3 to the 2nd power is 9. That means 3 times 3. Or when you say 2 to the 3rd power is 8, that means 2 times 2 times 2, 3 times. So the little exponent tells you how many times you multiply. And you have 3 to the 3rd is 27. That's 3 times 3 times 3. So what we see then is that the number we raised was this, the base. The base right here, that's the scaling factor. And you raise it to the dimension. That's the exponent, was the dimension. And you get the number of copies needed. So good job picking that out. So we have S to the D is N. That's our definition for dimension. The dimension is the exponent that you raise the scaling factor to get the number of copies that you need. Let's just verify that this is true by doing, how about we take a square. Oh, you can pause and take a picture of this. This is your 7.3 activity, so you can put that in. Okay, put your name there. This is 7.3. I encourage you to upload those right away because sometimes students seem to get them in the wrong section, and then I don't know how that happens. Okay. So you can go ahead and take a picture of that and upload it. And then we'll go ahead and verify it. So we'll verify that this is going to work by picking a square and making it 4 times as big. So if we make a square 4 times as big, we should be able to predict how many copies we need. So the scaling factor is the 4. The square is 2 dimensions, so that's for the D. And that should give us how many copies we need. So the scaling factor is 4. The dimension is 2. 4 squared is 4 times 4, which is 16. So we should need 16 copies. Let's just take a look and see. So here's my square. Make a square 4 times as large. So to make a square 4 times as large did need 16 copies. 4 rows of 4 columns of squares. So this is our general formula for calculating dimension. One way to calculate dimension. Dimension is the exponent you raise the scaling factor to get the number of copies you need to make figure that size. Well, fractals then, let's take a look at some fractals and see what dimension those are. Let's start with the Koch curve. Now you drew the Koch curve together with me in class, so hopefully you're pretty familiar with how it's constructed. Remember we took 4 line segments, and when we shrunk those 4 line segments down and replaced each of the 4 line segments with those 4 line segments. So then we had 16 line segments. And then we shrunk down the initial stage again and replaced each of these 16 line segments with the shrunken original stage. That gave us 64 line segments. And we kept going like that, and as we do that infinitely, that gives us the Koch curve. Here I have a large Koch curve, and I have some small Koch curves, okay? How many of those small Koch curves do I need to put together to make a large Koch curve? Anybody see? How many small Koch curves to make a large Koch curve? Yes, 4. Good. So I actually have 4. Okay, so we need 4 copies of this smaller Koch curve to make the large Koch curve. Now, how much bigger is the large Koch curve than the small Koch curve? Is it twice as big, 3 times as big, 4 times as big? So we'll measure as with a ruler. Okay, we'll measure with a ruler. We'll just measure length. It's not a very nice measurement. It's 23.2. Let's try if it comes out nicer in inches. No. I think the one in the book has a nice measurement. Let's try the one in the book. This is better. This is 9 centimeters. That's a nice measurement. Okay. So it's 9 centimeters. How big was the small Koch curve that I used 4 copies of to make the large Koch curve? You see on there? How big is the small Koch curve? It's just 3 centimeters, right? Goes from 0 to 3. So the large Koch curve is 9 centimeters. The small Koch curve is 3 centimeters. That means that the large Koch curve is 3 times as big. So the scaling factor is 3, which makes sense because remember when you were making this and we took out the center third and we replaced it with these 2 peaks? So you have a scaling factor of 3 here to take this little piece, put 4 copies down, and make this large Koch curve. So the scaling factor is 3. We're making a Koch curve that's 3 times the width of this little Koch curve right here. The number of copies we needed? 4. 1 copy of this little piece, then another here, here, and here. Because just like you constructed it on those 4 separate line segments originally, there's 4 copies of the Koch curve within itself that are quite large copies. There's lots of copies of the Koch curve within itself, but if you look at the biggest copies, then there's 4. Okay, so let's find the dimension then. So we're using S to the D is N. This, by the way, you should write on your 3x5 card, okay? For quiz 3.
When is quiz 3 going to be?
Quiz 3 is on either December 16th or December 18th, depending on what the registrar's office says. So the registrar puts up a schedule for final exam, so everybody has 2 hours for their final exam. Your final quiz it's not any harder than the other quizzes. It's not cumulative. It's just that we do have 2 hours, so we might as well make them available to you, okay? Okay, but on that quiz, you're going to use S to the D is N for a fractal. So we're going to look at different fractals today and make sure you know how to do that. So D is what we're looking for. We're looking for dimension. So scaling factor 3, dimension we're looking for, and N 4. We took 4 copies. So take out your calculator. You'll need an exponent P on your calculator for this quiz. So it's not 1, because 3 to the 1 is 3, so D is not 1. D is not 2, because 3 squared is 9. So we need some exponent between 1 and 2. So the dimension of the Koch curve is going to fall between 1-dimensional and 2 dimensions. 1 dimension and 2 dimensions. So how about 3 to the 1.5? That's not 4. That's a little too big. So I need a smaller exponent than 1.5, but bigger than 1. So let's try 3 to the 1.25. That's closer to 4. You should be able to get within 2 decimal places. Let's see if I can get a little closer. How about, what do I get if I say 3 raised to the 1.3? That's a little too big. So I need something between 0.25 and 3. Between 1.25 and 1.3. Yes?
3 to the 1.27.
1.27. Very nice. Look at that. Within 3/100ths. So on a quiz, you could use either 3 to the 0.25 or 3 to the 0.27. I'd like you to be within 5/100ths of the correct.
Or 1.26.
What did you say? 3 to the
Raised to the 1.26.
1.26? I think that might be a, oh yeah, there you go. There's 1/100th. Okay. Okay, good. That's even closer. 1/100th away. So a little bigger than one dimension. It's that little fuzziness gives it a little thickness, but not 2 dimensions. So fractals fall between the dimensions. Instead of being a whole number dimension, fractals can be fractional dimensions. There is a formula to do this exactly if you have the natural log button on your calculator. See, I always generate it. You don't have to know how to do this, but to find the formula, you'd use some logarithms from pre-calculus class. So the dimension can be found with the formula the natural log of n divided by the natural log of s. So if you have those natural log buttons on your calculator, you can use this formula instead. And then you don't have to sit and do the guess and check. I have to get it clean, excuse me. Let's try another fractal. Does anyone have any questions on finding the dimension of the Cope curve? Okay, how about the Sierpinski triangle? Actually, let's do the Sierpinski carpet. We'll leave the Sierpinski triangle for you to do on your own to make sure you know how to do this. Let's do the Sierpinski carpet together. That's a little harder. So here we have how the Sierpinski carpet is formed. You start with a square and remove the center square. That's 1/3 is wide as the whole square. And what that does is it creates squares around the outer edge. So you take each of those squares and do the same thing. Remove a square that's 1/3 as large as the whole square. And then you continue doing that. So that creates squares around the edge. You remove squares there. So the Sierpinski carpet is created by removing space. And we're going to find the fractal dimension. So we need to know the scaling factor and the number of copies needed. So if I have this square right here, and I want to make this big Sierpinski carpet as copies of this square, how many copies of this do I need to make this whole big thing? And how, what's the scaling factor? How much bigger, as measured by a ruler for width, how much wider, you could say, is the whole square than this square? It might be easier to see in the middle version. Okay, so I'm starting with this corner and making this whole thing. How many copies do I need of this corner? Anybody? Well, you can count them out. Okay, so we have this, there's 1, 2, 3, 4, 5, 6, 7, 8. We don't need one in the middle, that's empty space. So if you take this corner and make copies of it, you need 8 copies. Okay, 8 copies of this to put the whole rug together. And then you can see how much wider it is. Here you can just count off. So there's this original size going to this original size. How much bigger is the whole carpet in width compared to this little piece? What's the scaling factor? So this whole width is 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. And this is 3 squares. So not 3 times as big. 3 times this 3 squares to get this width. 3 of these wide. Okay? Scaling factor 3, number of copies 8. So let's go ahead and write that down. Once you have those figured out, then you can figure out the dimension. So we have the starting formula, s to the d is n. Scaling factor is 3. We need 8 copies. So 3 to what power is 8? Now this time we don't want an exponent of 1 because 3 to the 1 is 3. But we don't want an exponent of 2 because 3 squared is 9. So that's not quite, that's a little too big. So 3 to the 1.8, let's try that. That's still a little too small. 3 to the 1.9, that's a little big. 3 to the 1.85. Anybody closer than I am?
1.89.
1.89? Oh, that's very nice. Okay, thank you. So the dimension is 1.89. So, you know, when you compare the two curves, the Sierpinski carpet looks closer to 2 dimensions than the Koch curve. The Koch curve looks closer to a line, and the Sierpinski carpet looks closer to a square. And in fact, we see that their dimensions are reflective of that. This had a dimension closer to 1. This has a dimension closer to 2. Well, I'd like for you to try one of these yourself, okay? Finding the fractal dimension. So I'll leave the triangle here in the picture, and I'd like you to work on that. I'll come around and see how you're doing. So find the dimension of the Sierpinski triangle. You'll need to find the scaling factor and the number of copies. So as you're doing that, you pick the largest subcopy that you can that's similar to the whole. Remember, fractals have a sense of self-similarity, so pick the largest piece of this that's like the whole shape. I'm going to put my working picture upside down because it doesn't fit the other way. Or I'll put my ruler in the picture too. I'm going to have to lay it on its edge. Ah. There. Okay. So what do you think? Should be perfect. Then do you find D? You don't need to do a lot. Like you did with this one. So maybe you can work on that. If you're stuck, raise your hand. So the scaling factor, you each from your ruler there. So how big is, how big was the subcopy that you used? So use the little one, okay. Use the biggest one you can. The biggest subcopy you can. Yeah. Okay, so the subcopy is 6, and then how wide is the whole thing? So what's the scaling factor? And then if you use that biggest 6-centimeter one, how many copies of that? Well, you don't need one in the middle. The middle thing.
What do you mean no? Oh, you go from the 3 and you go to the 10. That's 7. No.
Okay, I didn't check the dimension of these.
Oh.
So use the biggest one you can. Use the biggest piece of that. So how wide is the biggest piece that you can use to make copies of it? So that would be the whole thing. So it's right smack in the middle there. What's in the middle? Well, it's split over a bit. It's closer to 6. So the 6-centimeter triangle is the biggest one. So that's the edge. So if you use that one, how many copies? So I did not get around to everybody. Feel free to see me after class or email me. Feel free to email me if you're online. So the width here is 12. Use the biggest sub-triangle that you can, which is 6. So when you use this one that's 6, then you need 1, 2, 3 copies because the middle is empty. This is emptiness. So 1, 2, 3 of these pyramids put together. Scaling factor of 3, scaling factor of 2 because it's 6 centimeters for this, 12 centimeters for the whole thing, and 3 copies. Oops, Sierpinski triangle this time. Scaling factor 2, number of copies, 3. When you use S to the D is N, you have 2 to the D is 3, and D comes out, I imagine, to 1.59 because I saw a number of you had that. So yes, the dimension is 1.59. So fractals fall between the whole dimensions, and now we have a formal definition of dimension. Next class, we're going to look at how we get those very beautiful fractals that our Mandelbrot and Julia sets. So bring your thinking caps for that. That's a little tricky. I'll see you on Wednesday.